Welcome. Today's lesson is entitled Solving Exponential and Logarithmic Equations. We've been working with these two families in the context of expressions, with functions, and now what we want to do is go ahead and solve some one-variable equations here in either form, be it logarithmic or exponential. And so some strategies to take a look at, of course, as usual with something like this. So you can kind of take these for what they're worth, but I'll reference them as I go through the process. If I can ask you, please, can you go ahead and highlight number 1 there? I had mentioned that this is probably one of the more important little skill sets for this unit, just being able to convert the equation from one form to the other, either exponential to logarithmic or logarithmic to exponential. So I will be going ahead and focusing on doing it that way. If you happen to remember a different approach from Algebra 2 and you like that approach, I certainly won't stand in your way. It's great. It's really the same ideas. Don't forget logarithmic properties. We can combine or separate logarithms just based on the properties that we've seen. Those who have a TI-83, you'll be doing a lot of the change of base formula. If you have a TI-84, again, you have the opportunity to go ahead and just type it in as is. And just check answers. Make sure everything works, especially on the logarithmics. So what are called extraneous solutions, meaning you did all your math right, but it might not work in the original equation. So just on the logarithmics, you have to be a little careful. Well, why don't we do a set of logarithmic equations, as you see on your paper, and then a set of exponentials, maybe a couple of word problems here and there, and then we'll round this out. But just good old-fashioned algebra here. Nothing should scare us too much. Let's go ahead and start out nice and easy with example 1, this logarithmic equation. And you see the dilemma at hand here. The variable that we're trying to solve for is part of the input of this logarithm. I guess the best way for me to say it is it's trapped as the input of this logarithm. I need to free it up so I can solve for it. The approach that I use, everybody, is the rollover. It's just, I like it. But again, if you remember a previous way and it just registers a little better, that's fine. No big deal. So guys, I'm going to take that 2, and I'm actually going to roll it on over to the other side, just like I've done before. And so this equation, which is in logarithmic form, can be written also in exponential form, and it would be equivalent in nature. So I roll that on over, the 2 bumps up the 5, and I get 4 plus 3x equals 2 to the 5th. And in my opinion, 2 good things happen when you just do that rollover. Number 1 is the variable that was kind of stuck as the input to the logarithm. It's now kind of freed up here. We just have this nice little linear piece, 4 plus 3x. That's great. It's free. Also, on this other side, 2 to the 5th is just a number which I can just go ahead and evaluate and get 32. And that is an equation that we should be very comfortable with. And so I'm going to go ahead and subtract the 4 and play it out. 32 minus 4 should be 28. I'm going to go ahead and divide by the 3. And 3 doesn't go evenly into 28, but that's all right. I'm just going to write it as 28/3 and sort of be happy with that piece. And it's kind of that simple when you get something along these lines right here. If you roll it on over, if you change the form, all of a sudden the dilemma that you were facing in the original problem kind of goes away. And that's why I like that. Cool. So that's example 1. Look that over, make sure it registers, but I really wanted you to master that concept of rolling it on over and changing the form. By the way, I had said check your answer, of course, especially for the logarithmics. This one does work. I'm going to shortchange that for just a moment. It does work. I'll really show you when we need to be careful. All right, example 2. We're going to do something similar in nature. I'm going to roll it over, but I am not ready to roll it over yet because I have 2 logarithms, really the sum of 2 logarithms on the left-hand side. And I guess the question I would have for you is, can we work with this? Can we manipulate this expression here to make it a little more compact and then potentially a little more user-friendly solving this equation? And this is one of the properties that we saw over the last couple days, is I can add 2 logarithms together in the same base. And so that's what I'm going to do. I'm going to add those 2 logarithms, base 4. The way I add 2 logarithms together is by taking the original inputs and multiplying them. So I would get x times x minus 3. So that is what's called the product property for logarithms, and we kind of explored that in detail. We proved it, all that good stuff. All right, nice. Let's keep it rolling. No stupid pun intended. Gee whiz. All right, so I'm going to go ahead and take that 4. I like circling it. It's going, it's going, it's going. Let's bump that on up. So when this rolls over, 2 good things happen. I just get 4 to the first, and I'm hoping at this stage you can see that 4 to the first is just 4. So just rolling that over, pushing that up, 4 raised to the first, and there's your 4. Now this was freed up, which is absolutely outstanding. I do probably want to go ahead and make sure I put it in standard form first before doing anything else. So I'm hoping you see that that's x squared minus 3x. And notice what happens essentially when you roll that on over. You change the equation, which was logarithmic. Now it's quadratic, everybody. Kind of cool. And I can solve a quadratic. Been solving a ton of quadratics this semester where I just set it to 0. If you want to go ahead and do the quadratic formula, that's fine, but this is pretty straightforward. How does an x minus 4 and x plus 1 equal 0 sound to you? And as a result, x is 4 and x is negative 1. And at first glance, that looks great. I did all my math right, and I should be ready to go on to the next problem. But we do want to be a touch careful. And so we do want to check our answers. Because what happened, as great as it was changing this to a quadratic equation has different conditions than a logarithm does. And so what I mean by that essentially is if I go ahead and put 4 back in, log base 4 of 4 is fine. Log base 4 of 4 minus 3, which is 1, is fine. Actually, this would be 1, this would be 0, and 1 plus 0 is 1. This works, long story short. But the question is, what happens here? When I try to put negative 1 back into the original, hey everyone, can I do log base 4 of negative 1? Is that an operation that is legitimate? No. And so what happens is you get something that works in the quadratic, which doesn't have any conditions to it, but it didn't work into the logarithm, which has a very, very straightforward condition. You can only take the logarithm of a positive. So just make sure, check your answer. This can be negative right here, but it's when you put it back in that you need to make sure that the input is positive. Okay? So just make sure it works. That's our answer. Cool. Actually, I'll start boxing all these up, so let me go back and do that one, and let's move on to example 3. Example 3 is sort of a redundancy, but it's a good one just to refresh on the properties of logarithms. I can add 2 logarithms together. I can also subtract 2 logarithms together if they're in the same base, which in this case they are. So let's see what we have going here. I'm going to do log base 4. And how do I deal with subtracting logarithms? What do I do to the inputs, everyone? Well, divide those inputs. So x plus 2 over x minus 1, and that equals 1. So I hope everyone kind of remembers that piece, what's called the quotient property for logarithms, and that's exactly what I do right here. I create that. Now let's go ahead and roll that on over. It's going to be something similar there, but when I roll that on over to the other side, I do get 4 to the first. Again, I'll go ahead and do this piece just in case. So push that on up. You get 4 to the first, which is 4. And so here you get a rational equation. That's kind of interesting. I don't think we've explored these in too much detail, but shouldn't be too bad. What do you say we go ahead and bring that x minus 1 on up and just treat this as a nice little cross-multiplying thing, or a couple different perspectives on it. But long story short, I should get something like this. Bring that on up. Hope everybody is comfortable with that type of mathematics. And then x plus 2, 4x minus 4. And let's go ahead and make this happen. I'm going to bring that x on over. 4x minus x is 3x. I'm going to add that 4 if it's okay with you in the same breath. And 2 plus 4 would give me 6. And so we end up getting just x is 2. So it's kind of cool. You actually changed this equation a couple times. It was logarithmic here initially. Then it went rational when I moved that 4 on over to the other side. Then when I brought it up, it becomes linear, and I get my solution. So again, I should check. Now, as long as when you put this back in, it makes the input of both of these positive, then chances are you did it correct. So in this case, 2 plus 2 is positive 4. That's good. 2 minus 1 is positive 1, so that's good. And by the way, if you did check the math there, it does work. And so there you go. You get just a single value right there. Pretty clean, pretty straightforward. I like 2 and 3. They're good ones. Okay. What do you say we do one more logarithmic equation here? Let's go base e. A lot of work that you do with exponentials and logarithmics in base e, so let's see if we can solidify the algebraic skills on something like this. Same deal. My variable is stuck, so let's just kind of remove the layers and see if we can get that free and ready to solve. So my first order of business is I can't do a rollover until it's a single logarithm and then that's it. So I guess, long story short here, I'm thinking you probably want to go ahead and subtract 6, you know, just good math, something like that. Now you do have a couple options with this 4, by the way, and either one would work. If you remember that nice logarithmic property, this 4 is actually the exponent to this right here. You can bring that 4 on up if you'd like. I think it's a little cleaner, to be honest, as a factor of 4 out in front in an equation to just divide by 4. Let's get rid of it just once and for all, because then it's going to go away and I get natural log of 3x minus 1 equals 3. So again, a couple different avenues to pursue. You know, you just decide what works for you. Okay, well, it's time. I do have just the natural log of 3x minus 1. I undid the plus 6. I undid the multiplication by 4. Now I'm going to have to sort of get this out of the way, free it up. And the way we've been doing that is changing the form. So, you know, I would ask you this, of course. What is the little base right here, even though it's not written? Should be base e. So I'm going to roll an e on over to the other side. When the e rolls over to the other side, it pushes up the 3. And I get my nice irrational number, e to the 3rd. And that 3x minus 1 is free as can be. Beautiful. Now, I don't know if you remember kind of in geometry, you probably worked a lot with pi, and your teacher probably said something like, oh, keep it in exact form. That would be just keeping pi there. Or you would multiply it out and get a decimal approximation. Same thing with this. You know, if you went exact form, you would just keep e and go the rest of the way. Or you could start working on the calculator and getting e to the 3rd. I would actually argue for most of these, really in all the applications, having it in e doesn't make a whole lot of sense. But actually getting the calculator to do this piece and then solving the rest of the way, I think the decimal approximation, long story short, just has a little more meaning. So I'm going to actually find what e to the 3rd is and then go the rest of the way. I hope you all agree, by the way, because I'm going to try to do this on my calculator in one shot. After I get e to the 3rd, are you okay if I add 1 and then divide by 3, and that'll get the x by itself? So I'm going to do that. If you want to go ahead and beat me to it here, that would be great. But I'm going to go ahead and type in e, and remember that nice button down here automatically raises it because it knows it's the base in an exponential function. So in this case, we just have our e to the 3rd. And what did I say? I was going to add the 1 and then divide by 3. So I'll do that and then divide by 3, and we end up getting something along those lines right there. So just want to make sure I have mine correct. So yep, I do want to add the 1 and then divide by 3. And so we get x is equal to, I'm going to go about 3 decimal places out, and I get x equals about 7.029. Yeah, I'm pretty comfortable with that one. That looks really nice. So that does basically wrap up our set with logarithmic equations. Take a look at those and make sure you're fairly confident and able to solve all those. Let's move on to the exponentials. The good news is the strategies are basically the same. So I am going to do a rollover. We just want to make sure our power is isolated before I do that. So I'm going to jump right into example 5. And I guess the one thing I'm going to do here, though, is add the 7 first. So nice and straightforward. If you could, please, add that 7. I get 6 raised to the 3x minus 4. 2088 should suffice. Now, just like the last set of equations, I do have a little dilemma here. The variable that I want to solve for, unfortunately, is stuck as the exponent of this particular power. I need to free it up. And the way I free it up, everyone, is to do the circle and the rollover. So I would take that 6 and I would roll it on over to the other side. And the good news is when you do that, you get something that is equivalent in nature, but quite a bit more user-friendly, because that 3x minus 4 is no longer stuck. You free it up, it jumps on down there. And remember, as soon as that crosses the equal sign right here, it changes from the base to this exponent to the base of a logarithm. So it's log base 6 of 2088. And that's great. Two good things happen. This is ready to go. Now to get the variable, all I have to do is add 4 and divide by 3. And another good thing is this is just a number right here. This is a constant. And so remember what this constant means, by the way. When I see log base 6 of 2088, what it basically is saying is 6 raised to the some power, something, 6 raised to the something is 2088. Well, let's find out what that is. I'm going to have to do my change of base formula, and I'm just going to go ahead and refresh for those who have a TI-83. It's log of 2088 over log of 6. So log of the input divided by log of the base. So that's what this is right here, and that's what I'm going to go ahead and type in on my calculator. I'm going to get that for us. And let me come back over here a little bit. So just be careful how you type it if you have to do it this way. Log of 2088 divided by, and notice I closed that parenthesis, log of 6. And I get about 4.266. So when I asked you, 6 raised to the what power is 2088, that's the exponent. Remember, the answer to the logarithm is the exponent for that particular base. Great. And now I just need to go ahead and solve this. Pretty much can do this in my sleep. Let's add the 4, divide by the 3, end of story. Let's go ahead and get that. In fact, I have this written on my paper if it's okay with you. I'm going to go ahead and do that without the calculator work there. I'm getting about 2.755. And that's looking pretty good. Remember, just if you have an 84, check in with me. Some of those 84s do have that nice ability to evaluate any logarithm on it. So just let me know, and we can explore that together. All right, good one. Let's do 6. Another base e. So this one I think works out pretty nicely. I've got my e to the 2x. There's the issue. The x is part of the exponent. Let's clean it out. But first order of business, guys, let's divide by 7. Again, just isolate the power. That's the key. Those are going to cancel. E to the 2x equals 9. Now this is great. It's certainly an advantage to working in base e, because now all I need to do is roll that on over to the other side. So the e rolls over. I'm going to go ahead and circle and do the rollover. When it rolls over, it changes into the base of a logarithm. And so it would be the natural log of 9. Wonderful. And this is a pretty nice, simple step even for me on my TI-83, because I'm going to just take the natural log of 9 and then divide by 2. And that should give me my x value. No change of base necessary here. So I'm going to go ahead and do exactly that. Here's my natural log button. So natural log of 9. And I'm going to go ahead and hit enter on that, but that would be the natural log of 9. And then what did we say we needed to do here? Divide by 2. So let's go ahead and divide that by 2. And we should get that answer right there. So just under 1.1. So let me see what I have there. About 1.099. Nice. And again, I would prefer this answer than just ln of 9 over 2. So this would be a decimal approximation as opposed to the exact, but I like it regardless. Okay, very nice. So we're working pretty well here with just sets of logarithmics and exponentials, and being able to solve for the variable that is somewhat stuck in a position that's not very user-friendly. And so we need to clean that out and get it in a position where we can solve it. All right, let's go do 7, a little refresher on compound interest. So here we go, 2 steps. And as a matter of fact, even before I think about it, can you go ahead and draw just kind of a little vertical curtain, kind of right in the middle there? That would be great. And let's see, $1,000 is invested into an account paying 8% compounded monthly. How long until it reaches $2,500? What if that account was compounded continuously? So 2 parts. So monthly, here's what I'd ask you to do. Do you remember the formula for compound interest for everything but continuously? And I remember it as A is equal to P times 1 plus R over N raised to the NT. Just be careful about that NT. Most of the time I like that in parentheses. Now let's see what we have and let's see what we need. I'm starting with $1,000. That is the principal. It is 8% compounded monthly, so just be careful. But 0.08 is our R value monthly, so that 8% is divided 12 times over the course of the year. And we apply this growth factor 12 times per year for a certain number of years. And so actually that's what we're going to find. That, I think, is the unknown. And we want to know how many years it would take in order for this 1,000 to get up to the 2,500. And I think that's our equation that's in play here. All right. Let's see if we can do a couple things at once just in this equation, and then it should be able to roll nicely. I'm hoping you would all agree that this 1,000 has to move over. I think I'm going to have to divide by the 1,000. Now here's what's kind of interesting about this compared to some of the other stuff. In compound interest, you have this 1 plus R over N. It's all just numerical, right? Can I just find out what 1 plus 0.08 over 12 is? And let's get that as a nice cleaner number there. I will go ahead and start setting up one thing. When you divide, 2,500 divided by the 1,000 is 2.5. So that's good to go. I might need a little assistance on the other piece. So let's just find out what 1 plus, what is 0.08 divided by 12 going to give us. And so there's what I have, and you can go out as many decimals as you'd like. Obviously, the further you go, the more accurate this would be. You know, whatever, we'll do what we need to do. But I get 1.0067 essentially. So 1.0067, and I'm going to raise that to the 12t. So that's kind of, it's cleaned out, so to speak. Now all we have to do is get this variable by itself by doing what we've done before, and that, of course, is changing forms. Let's do that. Hey, guys, I'm not going to circle it, but you know it's rolling. Roll that on over to the other side if you would, please. And you get log. Get some crazy bases, but that's all right. The calculator is going to do the work for us on this. So log base 1.0067 of 2.5, and that's equal to 12t. All right, this, some way, shape, or form, we have to get this number. This is some constant here. You know, basically we're asking this raised to the sum power is 2.5. Well, I'm going to have to go ahead and do my change of base on it. So log of 2.5 divided by log of 1.0067, something like that. So I'm going to go ahead and get that from my calculator, see what that is. Don't forget, just be a little careful typing that in. That's the one thing you have to do. Make sure you close that first one off if you're doing the change of base. And 1.0067. I hit enter and I get 137.22. Okay, so 137.22, 12t. Let's divide by 12, and we're in business. So theoretically, this would be the number of months, but we want this as the number of years. So let's go ahead and divide by the 12, and I think we're in good shape. So I'll do this right here and get that, and we get about 11.43 years. And that's a good first step. I like it. Okay, I'm going to go ahead and box that up. Now let's play out the secondary piece momentarily and think about it for just a moment. What if this account was compounded continuously as opposed to monthly? I guess I would ask you this. Do you think that it would hit the 2,500 before 11.43 years or after 11.43 years? If it's being compounded continuously compared to monthly, well, interest would be earning interest at a faster rate, theoretically infinitely. And so if interest is earning interest faster or more often, then it should reach our 2,500 earlier. Is it going to be a dramatic difference though? No, no. Again, as we saw, the more we compound, it doesn't have such a dramatic impact. It does have an impact, but it's not dramatic by any means. So let's go ahead and play it out. And let's see what the numbers suggest here. So PERT, let it roll there. And same deal, start with 1,000. I want to get up to 2,500. That's good. E raised to the 0.08, that's kind of our effective rate that we're going to apply a certain number of years, and that's what I'm trying to find. So we start with 1,000. 8% is being compounded continuously, so this would basically approximate an infinite number of payments over the course of a year, and when that occurs for so many years, let's find out how long it would take to get to 2,500. Same deal, I'm going to divide by that 1,000. This one should be pretty straightforward to solve, like working in base E algebraically. And when you get to calc, you do a lot of work in base E as well. So let's roll it. It's going over. And I'm thinking just the natural log of 2.5. And that 0.08t comes on down, and it's ready. Hope everyone's okay. This step to me is the key. Can you roll that on over and get the natural log of 2.5 and see that that is ready to roll? So let's go ahead and do the two calculations here. So natural log of 2.5, I'm going to close it, and then I'll go ahead and hit enter there, and then divide by 0.08. And again, watch our answer. It should be close to this answer. Should be just a little less. And oh, that's interesting. Maybe because we rounded a little on the other one. So yeah, that's fascinating. I'm going to go ahead and sort of revisit that other one. So this one was 11.45 years as opposed to this one right here. You know, I'm going to modify this one again if that's all right with you. And I have a feeling it's just because we rounded this off a little bit. So I'm going to go ahead and just grab my calculator and do this. I'm going to just modify that answer so it makes me feel a little better about the theory that goes behind it. So I'm going to do this. So log of, and this would be 2.5, because I think we closed this off just a little too soon, divided by log of, and then I might as well just go ahead and do it like this, 0.08 divided by 12. And so we end up getting that, and then I'm going to go ahead and divide that by 12. And there we go. Now I feel a touch better. And again, I won't, you know, it just depended how we rounded there. If you round a little differently, kind of like I did here, I think I just rounded a little too early on that last one. So if it's okay with you, I'm going to change this answer that we had right here, again, just because it should fit the logic behind it. So this is 11.49 years compared to 11.45 years. And that just makes better sense. That's why I'm going to be a stickler about it and change it up, because continuously should get us there faster than monthly. And because I rounded too early, we didn't quite see that, so I wanted to go back and check. All right, I'll leave that as is at this stage. But as long as you're comfortable solving, and again, if you end up doing this, hey, no big deal. All right, let's go get the last one. So I have a little function here. This is an interesting one. So the function models the percentage of students who could recall the important features of a classroom lecture as a function of time, where x represents the number of days that have elapsed since the lecture was given. After how many days do only half the students recall the important features of the classroom lecture? All right, interesting. Hey guys, what do you say we box that up there? Kind of have an interesting memory model that is essentially decaying logarithmically, for the way I'm perceiving this. And after how many days do only half the students? So in terms of the percentage here, this would be the percentage of students. And I remember this model. So this is when we do 50%, which would be half the students, we actually do want to put in 50. And so I'll tell you that according to this model right here. So that's what we're looking at. After how many students do only 50%, after how many days do only 50% of the students recall the important features of the lesson? Okay, well, that's what we're looking for. Let's go ahead and solve it. So same deal. I've got to get this isolated. First order of business, I think, is to go ahead and bring the 95 over. 50 minus 95 should give us negative 45 there. Just careful with your signs, of course. That's looking pretty good. Ooh, I'm sorry. I missed a number there. That should be 30. There we go. Better. Nice. Now I'll divide by that negative 30. So try to make amends for you here. So I've got that, and I just missed that 0 initially, but there it is. So divide by negative 30, I get that. I'm going to come right up here, and I get 1.5, and log base 2 of x. Very nice. Now it's a base 2 logarithmic function, so what we're going to do now to isolate that variable to get it by itself, I'm going to roll that 2 on over to the other side. I'm hoping you definitely are comfortable seeing that piece. And that should be our answer, whatever 2 raised to the 1.5 power is. And so let's go ahead and get that from the calculator at this stage. And 2 raised, 1.5, and there we go. About 2.83 days. So what this model is suggesting, between 2 and 3 days later after an important lesson, half the students have forgotten it, or have forgotten the important features of the lesson. That's wonderful. Makes a teacher happy, huh? Okay, well, I'll put that in. And then how about this one? After how many days have all students forgotten the important features of the classroom lecture? Interesting. All right, well, if everybody's forgotten, that means the percentage who could recall it would be 0. So that's what we're looking for here. And we'll see how true to form this is. Let's figure out how many days, and yeah, let's see what happens. Same deal. Bring over the 95. Okay, so 95's going over. Let's see, I'm going to go ahead and divide by the negative 30 here. That's looking good. Negative 30s will cancel. Log base 2 of x, good. That's what I wanted. Ooh, let's see if I could pull this off. This is going to be 3 1/6. Okay. Well, again, just like the last one, I'm going to round. I'm hoping on this one I don't have to compare it to anything, so it won't come back to haunt me. But this should be this right here. Hopefully I'm doing my math right on that. I've got that. And then let's roll this on over. The 2's going over to the other side. So x equals 2 raised to 3.167. That is going to be our answer. So after how many days will all of you forget the great, beautiful, important features of this lesson? So let's see, 3.167, oof, about 9 days. And so let me bring that on up. 8.898 days. Goodness, that's depressing. Oh well. Good math. I like it. So take a look at all those equations that we've gone through, and you're comfortable at this stage working in either family, exponential or logarithmic, and being able to convert forms and isolate the variable, all that great stuff that goes into solving equations. Think of all the different types of equations you've solved over the years. It's just one more piece to that puzzle. Hey, great. Why don't we kind of wrap it up at this stage here and let me know as you practice these. There's some great ones along the way and some good applications, obviously, where you're going to need to be able to pull this skill set off and be successful with it. Thanks.